All right, good afternoon, everyone. Just a reminder, we have a midterm here on Friday. Any questions about that? Okay, yeah?
For questions that involve inverting a midterm or inverting a matrix, will it be like 2 by 2 or will that
Yeah, I guess if I wouldn't ever ask for more than inverting a 2 by 2. So yeah, you're not going to be allowed to bring in any calculators or anything, no phones allowed on the table. So all electronic stuff will be put away. You won't need any computational tools for this. I'll keep everything simple so you can do it by hand. All right. So yeah, coverage is units 1, 2, 3, 4, nothing about 5 or 6. You're allowed one piece of paper with handwritten notes on both sides. I say handwritten because in the past, I've seen students reduce all the lecture notes to tiny little things. And I don't actually think that's a successful strategy, but what you also miss out is you also miss out on the process of going through the lecture notes and going through them again now that you've understood all the material and sifting out what is important and what is not important and reinforcing those concepts in your mind. So that is the goal of making that note sheet, is actually really helps you study.
Can we handwrite them on our iPad and then shrink them down?
Sure, you can do that. That's fine, yeah. Just handwritten is the key. Any other questions? Okay, excellent. So, so back to where we were. We were working on our optimization chapter. Our motivating problem is to be able to do minimizations like this by writing our own algorithm to do it. This is not something we can do analytically, deriving it by hand. It's just impossible. But we can learn how to design algorithms to do it. And so, of course, scikit-learn does give us some algorithms, but it's important to understand what is actually happening with those algorithms. Okay, so we learned about the gradient. The important things about the gradient is that at the locations of these minimizers, the gradient goes to 0. Do you guys have questions there? You who are talking, you students who are talking, do you guys have questions? Please don't talk while I'm lecturing then, thank you. Okay, so that's the minimizer. The gradient also tells us the direction of the maximum increase and the slope at the solution. So last time, one of the things we talked about is the fact that in some cases we're optimizing a scalar, some cases we're optimizing a vector, some cases we're optimizing a matrix. So we want to be able to handle gradients for all these cases. So when the parameter we're optimizing is a vector, then the gradient is a vector, and it actually has exactly the same length. The gradient has the same length as the parameter vector w. On the other hand, if the parameter quantity that we're optimizing is a matrix, the gradient is a matrix with exactly the same dimensions. Similarly, if we were optimizing a tensor, which is like a multi-dimensional, like greater than 2-dimensional data cube, then the gradient would have the same dimensions as that. Okay, we went through some examples, and then we started talking about another use of the gradient, which is first-order approximation of functions. So we're going to start with the scalar case, or we started with that, and then we'll next do the vector case today and then the matrix case. So the scalar case is the simplest one. We started with the Taylor series of this function j, which is in general a nonlinear function. And we have a reference point, w0. So in this picture, we are basically coming up with an expansion of this function by using this point as the reference. And the Taylor series says that we can write that nonlinear function as a constant term plus a first-order term plus a second-order term and a third-order term and a fourth-order term and so on. And all those higher-order terms, we are grouping them together in this last term, which has this big O. And the meaning of the big O is that all these terms that are collected together here are at most a constant times this, which is the deviation squared, when that deviation is close to 0. So it's just a way of collecting all that complicated stuff and saying, we don't really care about the details. We just care that the absolute size or the behavior of this is no worse than quadratic around the reference point. Okay, so that's an important concept. Are there any questions on the big O concept? Because we'll be using that a bunch. Okay? Yes?
Do you always approximate the constant to be equal to 1 or
Approximate the constant equal to 1. I'm not sure what you mean. I would say in general, we never approximate something to be equal to 1.
I mean, when you say the O
Big O?
that was constant times epsilon square, what can the constant take value?
Oh, fantastic question. So you're talking about this constant C. So it's at most a constant times this. We have no idea what that constant is. We know there exists some constant out there, but we don't know what it is. We never know what it is. So that's a great question and a very important point. There's even another thing too. When we say when epsilon is close to 0, we don't know how close epsilon needs to be to 0 for this to hold. And the closer we are, the value of that constant might change. So that's the closer we are has to do with this delta here in this more precise statement, and the constant is C. And those, all we know is that there exist two numbers, C and delta, both positive, such that that holds. We don't know what their values are. So hopefully this is not telling us a lot of details, but hopefully what it does tell us is enough to get the job done, and we'll see that it is. It's going to be enough. We'll use it several times today. Okay, great. So this is the Taylor series. This is an equality. The true function, the complicated function is exactly equal to this. But then we can also approximate that function just by throwing away all those higher order terms. And that gives us this simpler approximation here. And the approximation is just the constant term plus the linear term. So in this picture, J, the complicated function, would be this curve. And then the simple one is the linear approximation, and you can see that that linear approximation exactly matches the true function at the point W naught. As you stay close to W naught, it's a pretty good approximation. But then, of course, if you go far away from W naught, it's a pretty bad approximation. And that in that case, epsilon is not close to 0, so we can't really say much about this. But the point is that we're focusing on the area around W0, and in that area, we can say something about the quality of the approximation. Okay, good. This is, of course, this is just the slope of the function at that point W naught. Sometimes we write the slope with prime. I'm sure that's familiar, but this is the more explicit notation. Okay, so that's the idea of first order approximation, at least in the scalar input case. Is this making sense? Are there any questions about this? Okay, so what we'd like to do now is generalize this to vector input functions. So we have a scalar output, but we have several parameters at the input, and in this case there's d of them. And so what we're going to do is we're going to, again, fix a reference point. We're going to call it vector, or boldface WO, and if you want to think about its individual parameters, that'd be like, we could call them WO1, WO2, all the way up to WOD. And we'd like to do a first order approximation, or we'd like to write the first order Taylor approximation of this function. So how do you think we do this? So the hint is it's going to be pretty similar to what we have here, except it needs to involve more parameters than one. Any guesses of how that's going to look?
J of O W0 plus gradient of J W0 summation.
Yeah, so that's right. So here we have a single partial derivative. Why don't we just take a sum of terms like this, where we look at the partial derivatives with respect to the different w's, and then just put a sum around them. And then we'll also need to do something similar here. We'll have for each of the individual elements in the W vector, we'll have one of these. Okay, so let's write this out. So we're going to have, the first term will be J at the reference point, which will be vector W W0, plus we'll have a sum, and I'm going to sum over j. J will index through the elements within W. And now I'm going to have dj evaluated at the full W vector. I'm going to have dj dwj, and then I'm going to have wj minus w naught j. And I'm going to have a big O term as well. But let's just pause there. Okay, so any questions on this first part? So you can see, like previously on the previous page, we just had one of these. Now we just have a sum of them over the different elements in the vector. Is that making sense? It's pretty intuitive, right? Okay, so how do we handle this big O term then? What do you think we're going to do here?
You added in the summation.
Yeah, we'll have a sum. So what happens when you have a sum of, if I sum these individual error terms squared, is there a way I can write that more?
Norm?
With the norm, exactly, a squared norm. So we're going to have a big O, big O on the norm of the difference between W and the reference squared. Okay, because that norm is the sum of the squares of the elements within those vectors, or the difference vector. Okay, so, all right, so this is the main conceptual stuff. The rest is just some linear algebra that we'll go through. Are there any questions about this part? That's the main idea. Okay. So, all right, so let's take a look at how we can write this a bit more concisely. So this thing here, you can recognize this as the jth element of the gradient vector. So we can write that like this. Here's the gradient vector. I'll put square brackets on it with a subscript j, and that means take out the jth element of that vector. So that's how we get this. We can also say that this is the jth element of this difference in vectors w minus w naught, right? So we can write this term like that. And the reason I'm doing this is just going step by step. So now you can see we have a vector here, and we're summing the product of the first element in this first vector times the first element in the second, plus the second element in this times the second element in this, and so on. And that's just multiplication of one vector times another, right? It's exactly this. So this is one vector, transpose the other vector. I think maybe it's more obvious if you start with this and you ask, how can I write that as a sum? You would write that like this. You'd come up with some dummy variable, whatever variable you want to use, and then you index through the first sub j times the second sub j. Okay, so is that part pretty clear? Any questions on that? Okay, and then finally, the last step is to say, okay, if I want to make this equality into an approximation, I can do that by ignoring this big O term. And now we just have this nice, simpler expression. And just sort of for a purpose of interpretation, or maybe another way to write this, you may have heard of the inner product. The inner product, in linear algebra, the inner product is a way of measuring the alignment, or you could say the angle, between two objects. And in linear algebra, which can be quite general, those objects can be quite general. So if you have two functions and you want to measure the alignment between two functions, you just have to define the inner product in the function space you're working in. Or if you have two matrices and you want to measure the alignment to two matrices, you just need the matrix inner product. In this case, we have real valued vectors By vectors, I just mean like one-dimensional list of numbers. And the inner product is nothing more than just A transpose B, if the inner product between A and B is A transpose B. Okay. How many of you heard inner products before? Okay, good. So if we were working with complex numbers, complex arrays, then this would no longer work. It would no longer give us meaningful outputs. You actually, in that case, need to conjugate. Usually you conjugate the first one. And so that would be the inner product for complex valued vectors. So you can see that the definition of the inner product actually changes depending on the objects you're working with. So that's why I'm saying this is the inner product for real valued vectors. Okay. And as we'll see, this inner product actually gives us a way of generalizing what we find to any kinds of objects. As we'll see, you always get this expression no matter what objects you're working with. In this case, we're working with real valued vectors. Okay. So at the end of the day, we now have the scalar version, and we have also a vector version of this linear approximation, or first order approximation. Okay. All right. Any questions on this? Okay, let's pause and use some of these tools we've developed to understand the gradient a little deeper, to actually prove something that we've mentioned several times, which is that the gradient tells us both the direction of maximum increase as well as the slope. So this picture sort of illustrates what I'm talking about. Here I have a surface. I'm just kind of taking a little piece out of a surface so that we can see what's going on. This is a curved surface, and you can see this is in 3 dimensions. We have these dimensions control where we are, and then this dimension is like the height of the surface, or the height of the function, j, if you want. You can call this like jw, and we can call this like w1 and w2. Okay, so if we're at this reference point here, which maybe we can call w underline sub 0, then you can see that this is the height of the function. That would be like the height. And you can also see that if you're sitting here on this surface and you want to go uphill in the steepest direction, you want to move this way, you want to move in this direction, because that is the steepest increase of that surface. So that is one thing the gradient tells you. It tells you which way to move. Now, if you actually measure the norm of the gradient, that will tell you the slope right at that point of that curved surface. So those are the two things, the direction of maximum increase and the slope. Okay, so is the idea clear? Okay, so let's try to actually prove this now with the tools we've developed. So we're going to use something called the directional derivative, which is a pretty intuitive idea. It basically, you start at the reference, and let's say we just take an arbitrary direction u. And so a direction, we can think of a direction as just a vector with length 1. This is going to point us in some direction. We don't know which direction it's pointing us, but it's some direction. And setting the direction vector norm to be 1 is just an arbitrary choice, because we're really just curious about where it's pointing, not like how long that vector is. Okay, so this is looking at what we would call the rise over the run. We're going to now move a total distance of epsilon, because this has unit norm. This moves us in a total distance of epsilon in the direction u. So that's how much we move. And then this looks at how much has the height changed versus how much have we moved. Okay, that's the directional derivative. Hopefully that is a sort of intuitive idea. So let's take a look at this. We can now use the Taylor series approximation for this guy. So this is going to give us, so we're going to have let's see. Okay, so I'm going to try to cram, I'm going to write small, try to cram in a bunch of stuff here. So we're going to have Taylor series, we're going to have j omega naught plus the inner product of the gradient of j at omega naught. That is going to be transposed times the difference between w, which has this form, minus the reference. And we have our big O term, which is how far are we moving. So let's again just try to, let me shift over. So this is essentially, this plays the role of W in the Taylor series approximation. So this whole thing here is that term. Right? So the Taylor series says it's the height of the reference plus the gradient transpose times W minus the reference, and then plus big O of the difference between W and the reference, which you can probably see is just epsilon u. So is it making sense how we got everything here? Just plugging in the definition from the Taylor series. Are there any questions on anything? I'm seeing some wrinkled eyebrows. So are there any? So if one of you has a question, probably somebody else has the same one. Don't be afraid to ask. No? Everybody's good? Okay. So now we can do some simplifications. Oh, sorry, I forgot to write this last term. This last term, I'll squeeze it over here. Minus j w naught. Okay, so now we can cancel a bunch of terms. So this first j w naught cancels with the last one. This w naught cancels with this one. And if you look at what remains in this first part, really just this, there's an epsilon here, and there's an epsilon here, and those will also cancel, right? Because we have this, because all this is gone in this first part, so these epsilons will cancel. You're just going to get this transpose u. So I'll write that on the left. We get gradient of j valued at w naught transpose u. We have one more term here, which is order of, let's think more about this second term here. So if you have this epsilon inside the square norm, you can pull that out of that squared norm, but it will square when you do that. So you're going to get epsilon squared times norm of u squared, and that's divided by epsilon. But this norm of u, we said, is 1. So that, we can forget about that. Okay, so how are we doing on this? Are we good with the first term? Any questions on that? What about the second term? So what do you think is going to happen now if I think more about this second term? What happens as epsilon goes to 0? Yeah, so this one, imagine epsilon is getting smaller and smaller. Here you have squared epsilon times some constant, Maybe you can write this as c epsilon squared divided by epsilon. So what's going to happen is this one is just going to be c epsilon for some c which you don't know. But epsilon is just getting smaller and smaller and smaller. So no matter what c is, as long as it's fixed, as epsilon goes to 0, this will eventually go to 0 for any c. Okay? So basically, this thing goes to 0. So as a result, this whole last term goes to 0. So let me put a big line there. This goes to 0. So all we're left with is this first part here. So in other words, and that is the notion behind, when you do these directional derivatives, you take an epsilon small step in some direction, and then you divide the change in height by epsilon. And you look at what happens when epsilon goes to 0. So in doing this, we basically found that this is our directional derivative. It's just the gradient transpose u. Yes?
What is u again?
So u is we're looking at the slope in some direction. We're just gonna move in some direction, any direction.
Okay.
We're gonna move in that direction. We're gonna keep it totally general. And so we're saying for any direction u that I move in, this thing, which is the directional derivative, always takes this value. It's just the inner product between the gradient at the reference and u. Okay, we're going to go a little bit further, but I just want to make sure that we're okay with what we have so far. Any other questions about how we got here? Okay, so now let's focus again on that first term, and we can use. I'll write it in a way that will look a little bit more complicated, but then we'll see why it's useful. So we're going to look at the norm of the gradient. Let's get rid of this. The norm of the gradient, and then I'm going to have the original expression here in the numerator. And then in the denominator, I'm again going to have the norm of the gradient, and I'm going to have the norm of u. So hopefully you'll believe me that this is the same, because remember, I'm multiplying and dividing by this norm of the gradient, so those cancel. And then the norm of u was 1, so I can sneak that in there too. And then this is what I had before. So I'm just writing this in a slightly more complicated way, but it's going to be useful in just a second. Okay, so question? Yeah.
Can you explain how the y came again?
How the what?
The y, the norm of y on the denominator?
Why?
It's u.
Sorry, these are all u's. We have no y's here. Yeah. Sorry for my bad handwriting. Okay. Everybody good? Okay, so what we have here is I've written this specifically to look like what you get in this Cauchy-Schwarz inequality, which I think you've seen. Basically, it says whenever you have something that looks like this for any vectors a and b, that this thing is always in the interval between 1 and -1. Furthermore, it says that if you want to maximize this, then that happens when a and b are collinear. They have to be pointing in the same direction. They don't have to be the same length, the same norm. They just have to be pointing in the same direction. Okay, so notice that that's exactly what we have here. We have a form like that. So it says that, okay, first of all, this thing is bounded between, or it's in the interval between -1 and 1. So that means when you look at this directional derivative, the largest it can be is exactly the norm of the gradient. Furthermore, if you want the directional derivative to equal the norm of the gradient, that happens whenever u is pointing in the same direction as the gradient itself. So that's telling us two things. Basically saying the maximum slope you can get is the norm of the gradient, and it occurs when you move in the gradient direction. So that's exactly what we were kind of setting out to prove to ourselves. The gradient tells us the direction you go to maximize the slope, as well as what the slope is if you move in that direction. You just compute the norm of the gradient vector, and that tells you exactly what the slope is. Okay. So we got this using our Taylor expansion, our big O stuff. So you can see, here's at least one application of why we're learning about this stuff. Cool. Is everybody good with what we have on this page? Okay. Okay, so it's understanding the gradient. So now, so we've seen this now for scalars, for vectors. Let's do it for matrices as well. So the approach is maybe what you would expect. What do you think is what's gonna be the key idea in moving to matrices? Now we have a whole matrix of parameters. So how are we gonna adapt our procedure? What do you think? Did someone say?
Look at both the rows and the columns.
Yeah, we have a double sum over rows and columns. Okay, so basically we start with the cost at the reference, plus now we're going to have a double sum. We'll use j and I as our variables. Could use anything really, but I'll just use j and I. And so we're going to have the derivative of j evaluated at the reference, but we're going to take the partial with respect to w. Let's see, what did I want to? Wij. And then we're going to multiply that times the deviation between Wij and the reference point, which we'll call that Wo, comma, ij. Okay, so here it's the same idea as before, just extended to two different dimensions of unknown parameters matrix. Is everybody okay with this? Okay, how do you think we're going to handle that last term? Same idea, right? We'll have double sum. And so if I have a matrix and I want to sum over the square root of the elements, we've seen this before. It's called the Frobenius norm. Squared Frobenius norm means you have a matrix, you look at the sum squared of all the elements of the matrix. So that is going to be big O of W minus the reference point. And this F here tells us it's the Frobenius norm, or the sum of the squares. Okay. So that's the idea. So now we have a little bit of linear algebra to do. So this might remind you of some of the things we reviewed back in Unit 0 that keep coming up as the semester goes on. So we'd like to write this in terms of matrices themselves. This, you can see, is actually the ith row and jth column of the gradient matrix. So here's like the gradient matrix, ith row, jth column. But you can also write it, as we'll see, it's going to be useful. I can write it as the jth row, ith column of the transpose, right? When I transpose a matrix, I swap the column and row indices. So if I don't have the transpose here, that would be ij. If I include the transpose, then I have ji. So that's writing the first term. This term, this is just the ith row, jth column of the difference of the W matrix and the W naught matrix. And finally, we have this double sum. Okay, so here's the next part is where it's maybe just a little bit tricky if you're struggling with linear algebra, but we want to write this more compactly without summations. So let's take a look at this inner sum. Look at this inner sum. So we're going to fix j and just look at what we have if I do the sum over I. So if I do that, so the way I've oriented things is I have on the inside of this matrix multiply, I have the same index I, which is the one I'm summing over. So that helps me do this matrix multiply. And then the other two terms, this and this, tell me which row and which column of the resulting matrix multiply I am looking at. Because this is just a scalar. That's all that is. It's just one scalar entry. So I'm looking at the jth row and jth column of whatever matrix product I have here. So let me write that out. So this equals square bracket. So the first matrix is the gradient matrix evaluated at omega naught transpose. The second one is this difference in matrices, W minus W naught. And I am extracting now the jth row and the jth column of that. That's like, that could have been on quiz 0, that problem. It's exactly the same stuff you were looking at back then. Right. Are there any questions on that? Is everybody good with that? Okay, so that's the matrix. Now what we're doing is we're summing across all the terms JJ in the matrix. In other words, those are the diagonal terms. We're summing across the diagonal. That's a thing in matrix algebra. It's called the trace. So the trace here, if you have a matrix A, that means you're just summing the diagonals. So the last step is just to realize this is just the trace of this matrix here. Okay, and everything else is the same. And then the very last step is we do the approximation by throwing out the big O term. And now, what's maybe the kind of cool part about this trace is it turns out that when you deal with matrices and you want to know the alignment between two matrices, we have this inner product between matrices. And the way that you do it with real valued matrices is you do the trace of the first transpose the second. If you want to write that out in terms of sums, it maybe is even more intuitive. It means you have these two matrices. It's like you multiply them element by element, and then you sum all those multiplications. That's what this is doing. Okay, but anyway, here's the trace of something transpose another thing. That is nothing more than the inner product of the first thing times the other thing. And so what you see is that this formula here has shown up in all the cases we've looked at. It also was exactly the same thing we saw with vectors. We had the inner product of the gradient vector times the difference vector. So the only thing that changed, or the only thing that changes, is the definition of that inner product. So this is always the formula. It's just how do you define the inner product. Okay, so we'll do some more. We'll do an example with this, but that's what we have now for the. If you want to do a first order approximation of a matrix input function, we have a way of doing that. Yes.
So are we guaranteed that A transpose B would be a square matrix?
Yes. So if you think about the trace, if I want to sum the diagonals of a matrix, it only makes sense to do that if I have a square matrix. If I had a rectangular matrix, like there's actually different ways you can even define the diagonal. So yeah, the trace is only something that we use on square matrices. And so yes, it's going to work out. Also remember that the gradient matrix has the same dimensions as this difference matrix, right? That's from the definition we said it has to have the same shape. So even if this is not square, you have something transpose something of non-square matrices, that is going to be square. So it all works out. Okay, good. So any questions on this? All right, so let's do another example. So let's look at this cost function. This is kind of just a contrived cost function, which is useful for a little exercise. So the first thing is, okay, we're going to want to do some calculus. We're going to want to take the gradient of this cost with respect to W. So I highly recommend, whenever you have matrices and vectors and you need to do calculus on them, to write them as a summation. If you are an expert in vector calculus, you might know a whole bunch of identities you can use to avoid that. But I'm guessing none of you guys are experts in vector calculus, so I would say if you're not, write as a sum. That's the first step. So we need to write this as a sum, or actually as two sums, right? Because we have two different multiplications going on. So the first question is, how can I write this as a summation? Let me just start by writing the summations out, and I will declare the first index to be j, the second index to be k. So then what else goes inside there? So let me ask, is Jingyu Liu here? Okay, yeah. So what do you think we have in this case after the second sum? I'll give you a hint, AJ, and then
AJ, is it WJK and BK?
exactly. Exactly. That's how we can write this as a double summation. So we have the A vector, W matrix, B vector. J is going this way. K is coming down this way. And so we're doing this, multiplication of this to get us down to this. Is everybody okay with how we've written it? Okay, so now that we have things written out in terms of individual elements, now we can do scalar calculus, which we all know. We've known how to do that for a long time. So in particular, let's look at this. Let's look at the gradient matrix, but let's look at the j''th row and the k''th column. The reason I'm writing little primes here is I don't want you to confuse these indices with these ones here. These are variables I'm using for this summation, just dummy variables I call them. These are like specific variables I'm targeting. I want to look at a particular row, particular column of this matrix, so I can't use the same things here. Okay, so let's say that I want to do this gradient. What's the definition of that? So how can we write that maybe in terms of the elements, W, J, K, and so on? Let's see, what about Sajjad Akirati? Sajjad here? No? What about Dominic Alexander? No? What about Anshul Amin? Okay, so Anshul, what do you think? How can I write this in terms of these elements?
So for that specific J prime, K prime.
Yeah.
A J prime.
Well, so actually, I just want to write the definition of this. So I just want to write like D something divided by D something.
Yeah, so del J of W equal del of W J prime K prime.
Exactly. All right, so that's the first step. So I think you were already on the way to the second step, so I'll let you keep going.
Yeah, so for that specific one, it would be AJ prime times BK prime.
Excellent. Okay, so that's what we have. That is the value of the gradient. If we look at the jkth entry, we get this particular scalar. So now that I have that viewpoint, I can go back to the matrix case, and based on this, I can write this hopefully in terms of the A and B vectors. So let me ask, is Ethan Garrett? Ethan here? Yeah. So how do you think I can write that in terms of A and B vectors? So you said A bar times B bar? Or you mean like A underline? Okay, close, but not quite, right? Because if they're both column vectors, like all throughout this class, whenever we have a vector, it has to be a column vector. I can't do matrix multiplication with two column vectors. Like they don't have the right shapes. How do I fix this? Yeah, which one? Okay, so if I transposed A, being a column vector, I would have something like this times this. And what's the size, what's the shape of that? Scalar, right? But I want this to be a matrix. So what do I need to do? Transpose B, exactly. The other way to understand that is, see over here I'm saying that J prime goes down the rows, right? So as I index through J prime, I see the different elements of A, I'm going that way. This is a column vector. On the other hand, K prime goes across the columns, and so it says as I go across the columns here, I should see the different B's, but for the same A. So if I go across the columns, you can see I go across, should be transpose. Now if I go across the different columns of this, I'll see the different B's, but I'll have actually the same A element. Okay, so this is the gradient matrix now. Everybody good with that? Yeah.
Before A, matrix A multiplied by matrix B, that would be,
I'm just writing a little picture to help visualize what's happening. Does that answer your question?
yes.
Okay, yeah. So yeah, and when we do this, we actually get a full matrix, right? Column times row gives us a matrix. Okay, great. So so now we have the ingredients to do our linear approximation. So this is the equation that we've derived on the previous page. Now we have the ingredients to plug in. So we have derived this gradient matrix. It is A times B transpose. So I've just plugged that in, but I have another transpose on that whole thing. So here with transposes, I've seen a number of you guys make mistakes in office hours. Remember that when you transpose a product of things, you have to transpose them individually, but also reorder the product. So whatever the product is, ABC, you have to swap them, become CBA. So in this case, it just means put B first. And when you transpose a transpose, you get no transpose, and then you have A second with the transpose. So hopefully that's pretty straightforward. Now, the coolest thing about the trace is this property here. As we know in linear algebra, it's non-commutative. You can't just swap the order of matrix multiplication. But when you have two things inside of a trace, you can. You can do it. So trace of B times A is the trace of A times B. And so what that allows us to do is it allows us to think of the second thing here and the first thing here. I can swap the order of those. And so now I put this B second and everything else first, and the traces of those two things are identical. Is everybody good with that? This is a super important property of the trace, and in fact, a lot of times we try to write things in the form of a trace precisely so we can do this little trick. We'll see that as the course goes on. So now that we have the trace of this, okay, what is the shape of that? I have a row times a matrix times a column. When I do that, what size thing do I get? Matrix, vector, or scalar? So it's, sorry, I didn't, let me just draw it again. Row, matrix, column. So the shape of this is a scalar, right? And if this is a scalar and the trace is the sum of the diagonal elements, well, there's only one diagonal element. Trace of that is just that itself. I don't need to use the trace. I can just remove the trace, and I get the scalar itself. Okay. Okay, so that is finally a simplification. And now that we've gotten there, you can see that we're going to have this term cancels this term, because we're going to have an A transpose W naught B. That cancels the first one. And all we have left is A transpose WB. So this is the first order approximation of J. And actually, if you look at how J was originally defined, it's identical. So why is that? Is it surprising that when we did the first order approximation of this or the linear approximation, we got the same thing? Does it make sense or not? It does make sense because this is a linear function of W. So when you do a linear approximation of a linear function, you just get the same thing. Okay. If this had nonlinearities in it, linear approximation would get rid of them. But this is just linear to start with. So after all this work, we just get back to the original thing. So really, this was just kind of an exercise, a contrived exercise, to go through some of the things that you do often. Whenever you want to do vector calculus, write things out in sums, then do the calculus on scalars. Then once you're done, pack them back into vectors and matrices. And then the rest is just step-by-step linear algebra using properties like transpose, trace, and so on. Okay, so that's this example. Right. Yes.
So in like step 2, when you did J prime, K prime,
Uh-huh.
and then just going from there to step 3,
Mm-hmm.
so how does it turn into a row and column? Step 3, I think.
So maybe it's easier to go backwards. So if I have this, which has this form, right? And now let's say that I want to look at a particular element in this matrix. I want to look at, this would be like the J primeth row, K primeth column. So I would then look at this side. So I'm going to find, that's going to involve this. And, and that's going to multiply. To get this entire row of the matrix, it'd be that value times all of these. But of that vector, I actually only want this element. So that means I'm going to look at the K primeth element here. And so now you can see it only depends on the product of those two elements. Yeah.
Thank you.
Sometimes it's easier to go backwards than forwards. But the more practice you get, the easier it is to go in the harder direction. Just going back and forth. Okay.
It sounds easy when you're explaining the output should be a scalar or it should be a matrix, but how to figure it out on our own?
Oh, just the dimensions themselves. So, like for any legal matrix multiply, the dimensions have to work. So whatever this dimension is, it has to be matched by this dimension. Whatever dimension this is, it has to be matched with this. But at the end of the day, once you've done all those inner multiplications, the only thing that remains is the outer dimensions, which is going to be this and this. Those are the only things left.
This I understood. In the third step, you say it has to be a matrix.
Yeah, so this is the entire gradient matrix. So we know that the gradient matrix has the same shape as the parameter itself. So we know that this must be a matrix. Anything else, there would be some sort of mistake. Yeah. But again, even if we didn't know that, and you just say, I have a column times a row. Okay, that's a valid thing because this dimension, which equals 1, agrees with that dimension. But now when I say what are the overall outer dimensions, it's going to be this by this, which is a matrix. Yeah. So this unit 6, we'll see a lot of that linear algebra really come back. We'll use a lot of it here. So it's important. If you feel it would be helpful, you can go back and review some of the unit 0 materials. Okay, great. So the other thing I want to do just very quickly is talk about how you implement this in Python, because there's a cool trick called NumPy broadcasting. Actually, there's really two things to talk about. First, there's how do you do vector matrix or matrix multiplication in Python. So there's different commands you can use, but I think the most efficient one is to use this dot. It's like a dot command. And it looks like this. So this is actually a vector, or A is a vector, and WB is a vector. So really this is a dot product or an inner product between A and WB. So that sort of makes sense that you can do this with A dot and then the WB thing. Now, even this you can do with a dot product. This is like sort of a dot product between every row in W and this B vector. But Python is smart enough to know that if you want that dot product, it just does them all step by step, and it gives you a column, or it just gives you a vector of those dot products. Okay, so this is how you can do it at the end. A dot quantity W dot B. That's the most efficient, least characters to do this. There's other approaches, but I think this is my favorite. Okay, is everybody good with this? Okay, so now this is the more interesting one. How do you do this in Python or NumPy? So what's the first thing to remember about NumPy is different than MATLAB in that when you have a vector, it's a one-dimensional quantity. There's no way to transpose a one-dimensional quantity because transposes are things you can do to matrices. To transpose is kind of like to swap the two indices, but if there's only one index, you can't swap it with anything. So it's not really clear, how to do this in Python then when A and B are these one-dimensional quantities. So it gives you this cool option to sort of temporarily think of them as matrices. So this is how you do it. When you do A, and then in square brackets, colon, comma, none, it sort of temporarily expands this into a matrix. It takes the values of A and sets them along the first column, but then it just copies that column as many times as needed to do the next operation. So let me show you a little picture. So this A none thing, you can view it like this. So here's the original A, which is just a series of these four numbers. Now when you do A column dot none, it sort of makes it a matrix with A as the first column, but it just copies the other columns one after the other. Now, with B, you're doing B none, comma, colon. It does the same thing, but now it puts B along the first row. So this colon sort of means like use all the rows for B. Or sorry, use all the columns for B. And it just expands them until these two things have the same size. So now they're both going to be that size. And now whatever operation you put in between them is compatible. You have same size quantities. So you can do a plus, which is what's shown down here. This is an example if the plus was there. Here we're actually doing a multiplication. That's what we want. So this is a cool trick, very useful, and this is how you can do this in Python. Another way that I kind of think about it is this sort of expands this from a one-dimensional quantity almost to a two-dimensional quantity that has, a column vector versus a row vector. Okay, but basically that's what we need to implement this, and the rest is like we're creating some random quantities, putting them through our function, and just plotting the output just to make sure it runs and we get something reasonable. Okay. So that's all I wanted to say for today. Are there any questions on this? By the way, there's a link here. This green link, if you click on this, it takes you to a NumPy document that explains all this stuff in gory detail. If you want to know exactly how NumPy does broadcasting, it's all there. And if you click on the none, it shows you where that's defined in the documentation. So I'll see you guys on Friday for the midterm. Please try to come a little bit. And when you sit, try to space yourselves out as much as possible so that I don't have to move you when the exam starts. Thank you.